Okay, let's talk about the fourth robot. The fourth Nephele robot. I've made several bad robots, and this is the fourth one. It's very sophisticated. None of it works really that well, but it's much better than the third, second, or first robot that I made. The steady progress is reassuring, although I have no working robots walking around doing my dishes for me. But one day. For the last 2.5 years, I've been designing and manufacturing this fourth robot in my little robot series. Designing and 3D printing the mechanical components of it, the linkages, the gearboxes. The robot's equipped with sensors for weight and torque angle at each joint, as well as the joint angles. I designed and built a custom motor controller driver board that takes a PWM and direction from a controller and converts that into the voltages out to the motor. So overall, it's been difficult and a struggle for sure. The fact that everything is just a little too mediocre means that the robot ultimately needs to be scrapped. So it's going to be back to the drawing board after this, but I wanted to share the experience of designing and building this whole thing and some of the lessons I learned along the way. I'm Josh Whitman, CEO of Whitman Technological. While I learned a ton of interesting stuff from all aspects of the robot, the motor drivers themselves actually work really well, and I can probably reuse this exact design in the future. When designing the motor drivers, I had a few requirements. It's going to take a speed and direction from an Atmega 328. The speed will be a PWM signal, and direction will just be a regular I/O pin. That means that the signals into the motor driver are at 5 volts. The motor that we're going to drive can run at up to 2 amps, and it likes to be powered at 12 volts. So that means the driver would need the following hardwired logic gates built into it. When the speed pin goes high and the direction goes high, the A pin has 12 volts and the B pin has ground. When the speed is high and the direction is low, the A pin has ground and the B pin has 12 volts. When speed pin is low, regardless of direction pin, A and B both need to be ground. Because the input signals are at 5 volts, we'll also need to make sure we transition properly to 12 volts. I had many iterations of the board, and by the 7th, I finally had a solution that worked really well. First, both inputs are going to run into some TRL NOT gates. That allows us to have the output of the NOT gate at 12 volts, even though the signal to switch the NOT gate comes in at 5 volts. The component that's actually going to push the current into the motor is going to be a MOSFET H-bridge, and that H-bridge is functionally a CMOS NOT gate. Immediately after each TRL NOT gate that brings the logic voltage up to 12 volts, I added a CMOS NOT gate that inverts it back so speed becomes not speed and then becomes speed again with CMOS logic at 12 volts. If we revise our table for the inverse of A and B, so that we know what signals we need to feed into our H-bridge, it looks like this. In CMOS logic, this is just a NAND gate. It's actually a pretty simple gate to understand. When both inputs go high, then the two N types will conduct, pulling the output low. If either of the inputs is low, then the N types won't be able to complete the circuit, and either of the P types will be able to complete the circuit, pulling the output high. At this point, for A, we need speed NAND direction, and for B, we need speed NAND NOT direction. And since that first TRL gate outputs NOT direction, we'll actually take the NOT direction from that output and pipe it into this NAND gate. Once we had all this logic properly laid out in our schematic, it was time to start designing the board. It took 12 hours of layout. I finally went to bed at like 3 in the morning, and I woke up the next morning and sat back down, and it was like another hour, and I had it where it required 0 jumpers. It was all the transistors on the board, everything connected, and it was beautiful. I was really pleased with the results of that. These little drivers work fantastic. These MOSFETs are only rated for 2 amps, but they don't even warm up. The gearboxes in this iteration of the robot are by far the weakest point. There's a bevel gear that allowed us to transfer the rotation by 90 degrees, and that drove one of the sons of a compound planetary gear. The bevel gear was like a 2-to-1 reduction, and the compound planetary gear was about a 30-to-1 reduction. At first, I tried building it using the very smallest teeth that I could print reliably and make just the smallest, lightest gear set possible. And that was too small and not robust enough for what I wanted to do. So I scaled it up a little bit more. I tried printing exclusively nylon gears, and the gear sets were just too spongy, a little too flexible. So I tried PLA, which is much more rigid but also more brittle. And I printed entirely PLA gearboxes, but those were very noisy and kind of scary. So what I ended up doing was printing just the planets out of nylon, and the suns and rings were in PLA. And that way, anytime teeth were meshing, it was always a nylon to PLA mesh. That seemed to work pretty well. I packed it full of lithium grease, and I assembled the joints of the robot. And as I was testing, the robot could swing. As long as it didn't swing its limbs very far, it could continue to move. But as soon as I would push it to try to lift its leg farther than was easy, they would get locked in that up position, and the motors couldn't reverse them back out again. As long as I didn't let it lock, as long as I kept it moving freely, then the gears inside wouldn't twist, and I could actually keep it swinging back and forth and get quite a bit of motion out of it. I bumped into the idea of lapping the gears, where you run them first, usually with a lapping compound or something kind of gritty. And I attempted to lap the nylon gears, which did not work at all. It just made them like really abrasive, and it was bad, like a Brillo pad. So I looked into other materials, and I came across polycarbonate, and I printed the planets out of polycarbonate, and I was able to lap those gears much better. So PLA and polycarbonate could mesh with each other, and I could lap them properly, and they would get nice and smooth. So I made this kind of bootleg lapping compound out of toothpaste, water, and rock tumbler grit. The finest grit, the 1200 grit polishing grit, is what I ended up using. I built a little lapping stand that I could put the gearboxes in and then run them back and forth at whatever speed was appropriate. And I eventually settled on lapping them for about 10 minutes with 2 minutes each direction, switching back and forth. That made the gearboxes run pretty smoothly, and I reassembled the joints with the new gearboxes in them. I attempted to lubricate one of these new gearboxes with silicone lubricant, and I compared it to a new gearbox with lithium grease to see which one would resist binding more. And it turns out the lithium grease was a superior lubricant than the silicone. 3D printing out of polycarbonate is actually not that bad compared to nylon. They both print at about 270 C. And the bed temperature for nylon, I could get away with 100 C, but with polycarbonate, the higher I could get the bed temperature, the better. My printer won't go above 120, and it can't even stay above 117 while the printer is in motion. I had to modify my printer's firmware so that it wouldn't throw a thermal runaway error because the bed would stay consistently 3 to 5 degrees below the set temperature for the duration of the print. On each leg, I had a controller board that was responsible for reading the sensor data from the joints, as well as controlling the motors through the motor driver boards. Each controller board had a Mega 328. At first, I used the 28-pin through-hole version of that chip. Later, I switched to the 32-pin SMD flavor of the chip. I set up the motor drivers so that they would slot into sockets vertically on the controller board so I could take up more volume instead of more surface area. The controller board also had an ICSP header that allowed us to program the microcontroller's firmware by connecting a programmer to this ICSP header. The 3 wires that had signals from the microcontroller out to the sensor boards had terminating resistors. To eliminate ringing on those wires, that was the master clock, the serial clock, and the data out from the controller. There were 4 blue LEDs, one for 12 volts power, one for 5 volts power, and then the serial communication in and out. The microcontroller clock also needs a crystal with a pair of capacitors attached to it, and there's a 3.3 volt regulator with its own little capacitor. Throughout the process of evolving the designs of all the different parts of this iteration of the robot, I improved my manufacturing of circuit boards significantly. One of those improvements was making a 3D printed vise that I could clamp to my router, and it would hold the circuit boards in exactly the same position every time I reattached the board, which let me cut the traces, take the board out, apply solder masking, and then put the board back in and know that it would be aligned well so that I could drill and cut out the boards afterwards. As the solder became messier and messier and the components became more and more dense on the circuit boards, I really needed to start doing solder masking. I got some UV-cure solder mask, applied that to the surface of the boards. I would print the stencil for the solder masking onto a transparency. At first, I would just line up the transparency very carefully by eye and then put it underneath the UV light. But I kept bumping the transparencies and ruining boards that way. So I ended up taking my microscope and printing a little armature for it, so I could hold it above the stencil and carefully line it up from the perspective of the UV light that was going to be shining on it. I'm really happy with the way that my whole solder masking setup works now. It's pretty easy to get it right on the first try. The most baffling, painful part of Nephele 4 was the sensor boards. The job of these boards was to report the deflection of 3 bridges that attached each joint to the segments below. These bridges bend up and down as the load and torque on each joint changes. The deflection is relatively small, so we'll need some very sensitive mechanical and electrical components to detect it accurately. We put strain gauges on the top and the bottom of the bridges. When the bridge is bending in one direction, one of the strain gauges will compress and its resistance will decrease, while the other strain gauge will expand and its resistance increases. The Mega 328 has a set of analog digital converters, but those converters are 10-bit, which means they can report a voltage as a value from 0 to 1023. That's nowhere near enough precision to get an accurate measurement out of our system, so we're going to need a better analog digital converter. I chose a 24-bit Texas Instruments analog digital converter. These 24-bit ADCs give us a number from 0 to about 4 billion. I ended up using a 6-channel ADC. 2 of the channels were hooked up to Hall sensors. The Hall sensors would measure the field coming from a magnet attached to the joint. So to get the ADC to function, it's like a tiny little computer. You give it 3.3 volts to power it, and then you feed it a master clock signal. This is just a square wave that goes high and low. And with each transition, the transistors inside the ADC perform their math and computations and register shifting and all the other functions that it does in order to be able to output these digital representations of the voltages. The chip has a data-ready pin that goes low when all 6 samples have been collected and they're ready to be retrieved. We connect a light to this pin, and that allows us to see when the chip thinks it has data ready. On our sensor board, that's the green light that turns on when there's data ready to be collected. The Texas Instrument ADCs will talk to the leg controller through a protocol called SPI, Serial Peripheral Interface. SPI uses a series of 4 wires. There's the serial clock, which is a square wave like the master clock, but usually slower than the master clock. There's a data in, a data out, and a chip select. When the chip select goes low, that tells the ADC that we're actively trying to talk to it. On this chip, it looks for the rising edge of the serial clock square wave and uses that as the point in time when it will switch the output pin on its data out. The value of the data out pin can be read at the falling edge of the serial clock, and then a new rising edge is transmitted that tells it to change to the next bit. In practice, the SPI communication can happen very, very quickly. In reality, the wires that connect the controller and the peripheral act like resistors, inductors, capacitors. They have ringing, they require charging and discharging. They don't just instantly transition from 0 volts to the reference voltage. If the ringing is not addressed, then the bouncing up and down of the voltage as the clock signals change can appear to the analog digital converter like multiple pulses, and it will attempt to output bits for each of those ringing waves. With a handful of research and some help, I learned that you can mitigate ringing by using a terminating resistor. If you add a resistor with a value matching the impedance of the conductor, it will dampen the ringing almost perfectly. But there was a more subtle problem that I ran into that took a very long time to figure out. When the signal goes high from the controller, it essentially begins charging the wires that are transmitting that signal down to the sensor boards. When the controller sends a clock pulse going from ground to the high voltage, the sensor board is listening, and when it hears that voltage go above 0.8 volts, it says, I'm getting a signal now, and it runs its internal mechanisms that cause all the transistors to shift buffers around, move things in memory, switch the outputs on certain pins. And it turns out that the first 8 bits that you recover, these chips are just responding with the registers all intact. But as soon as we request the 9th bit, there's some internal function of this chip that's drawing a little bit of extra current from that clock in pin, and it actually pulls the voltage down at its end of the wire below the threshold of 0.2 volts to where it looks like it's a low signal again. Meanwhile, it's still trying to raise it to the maximum voltage at the controller, which charges it back up to 0.8, where it registers it as a high signal again. That was a mystery that took forever to uncover and imagine why it might be happening. And the way that I resolved that issue was putting a capacitor on each board that charges to the 3.3 volts these ADCs run at, and then a transistor connected to these signal wires. So when the signal goes high, it doesn't feed directly into the ADC. Instead, a transistor begins to conduct, and it functions like a NOT gate. The voltage is stored locally in the capacitor right next to the chip, and it has no problem pulling the pin high without these phantom fluctuations. So that resolved the issue of the 9th bit suddenly drawing a little bit of extra current and emitting like 5 bits where it should only be emitting 1. That was a problem that baffled me for a long time. Eventually we got there and they could communicate reliably with each other. As I did all of this, I amassed a terabyte of raw footage of manufacturing and assembling and soldering. And so I'm going to give you one final montage that shows working with these sensor boards and the robot as a whole. And then that's the end of the video. Even though this robot doesn't actually work, I would think it's a little bit of a triumph and also a little bit of a failure. I learned a ton. It was an awesome experience. I can't wait to start building the next robot. It's going to be better. It's going to be better than this one. Thank you so much for watching. I'm Josh Whitman with Whitman Technological. I love science, and I hope you do too.